Okay guys, in the previous lecture and the previous recitation class, we introduced Biot-Savart law. We introduced Biot-Savart law for a point charge, basically, which allows us to calculate magnetic field produced by a point charge. And also we introduced Biot-Savart law for a current. Right? So today we're going to use the last example, the last formula where the Biot-Savart law can be used to calculate magnetic field produced by a current. So let me draw the picture in order to refresh. So let's assume that if we have some arbitrarily shaped wire, right? And let's say with current I flowing that way, let's say. So, and let's say we want to find magnetic field at this point P. So what do we have to do? We usually, we're supposed to take infinitesimally small section of this wire, ds, direction of this vector is determined by the direction of the current. Then we need to know this distance from this infinitesimally small section to the point P, so that's our R, and then in order to make law look nice and a vector form, we need to introduce R hat, right? So as a result, we can write Biot-Savart law. It's basically contribution to the magnetic field at point P, which is created by this small infinitesimally small section of the current. So dB vector equals to mu naught over 4 pi, then current I, then ds crossed with r hat divided by square of the distance from the section ds to the point in question. So we can frame it, and today we are going to use this formula to calculate magnetic field created by reasonably complicated piece of wire. Right? And so now let me draw that piece of wire and calculate the magnetic field. Actually, the problem is 46 from chapter 29, problem 46. Right. 46. Right. Okay. First of all, I need to draw the wire, and it will be a reasonably complicated picture. So let's do this way. Right, so there will be first, first semicircle. You know, I can do better than this. Right? First semicircle. Right. Okay. Then there will be internal semicircle. Right. And then we connect them with these small straight sections. Okay, so some information is given. Probably first I should give information about the current flowing through this loop. You see, we have wire of this reasonably complicated shape, and we have current flowing. So current flows this way, counterclockwise. Right, this way, that way, and this way. So that's current. And the value of the current is 5 amps. So I equals to 5 amps. Then radii are given. So let's say this is R1 and that is R2. Okay, the values of R1 and R2 are given. So R1 is 1 centimeters, R2 is 2 centimeters. Okay, so what do we have to find? Magnetic field at a particular point. Of course, physics is quite simple. Right? So we have a wire with current. If there is a current, there must be magnetic field. The whole space will be filled with a magnetic field. Right? But we're going to find magnetic field at the center, over here. Right? At the center of both of these semicircles, right? Because at that point the system is going to be reasonably symmetrical, so as a result calculations are going to be reasonably simple. If somebody asks you to calculate magnetic field, for example, at this point, it will be significantly more complicated. Right? Okay, so now, all right, so what do we have to do? we have to apply that formula. We cannot use that formula which we used in the previous classes. You remember, magnetic field created by an infinitely long straight wire, because now we don't have infinitely long straight wire. So that formula mu naught I divided by 2 pi r cannot be used. So we have to use this form of the Biot-Savart law, which can be applied for any wire with the current. But of course, we will have to do integration. So we will have to integrate over this whole loop, right? And since the loop is kind of complicated, and plus, since integral is an additive thing, you can split integrals into as many integrals as you want, right? And in this case, I think it's obvious that we will have to split our integration into 4 integrals. The first integral is going to be over this small semicircle of radius r1. Let me label some points. Let me call this point, okay, maybe it's red. This point, let's call it A, this point B. So the first integral will be over this semicircle from point A to point B, and let me call this part of the loop as piece number 1. Then second part of the integral will be from this point C to point D over this semicircle with the radius r2. And I'm going to call this part of the loop as part number 2. And then naturally this section, let's call it number 3, and this will be number 4. So this will be number 3 and this will be number 4. Okay, so as a result the integral will be split into 4, and so there will be contribution to the magnetic field at this point from 1, from 2, from 3, and from 4. So we're going to have 4 contributions to the net magnetic field at this point. Let me label this point P, for example. Let me call it point P. Right? So let me write that we need to find what we need to find. We need to find magnetic field vector. Right? We will have to find direction and magnitude at point P. Right? Then now we have to just write down. So, and you know what? Before, let me introduce coordinate system. Right? Actually, z-axis. Right? You can pick any z-axis. You can pick z-axis out of the board or into the board. I'm going to pick z-axis into the board. It's a coordinate system. You can pick any coordinate system you want. Okay, so let me pick z-axis into the board. So in, it means cross. Right, so that will be my z-axis. Right, so that my final result will be written in a vector form. Right? Okay. And so now let's write our principle of superposition. So we have 4 components of the magnetic field. So I can write, so B equals B1, it's a contribution to the magnetic field at this point from the first section, plus B2 plus B3 and plus B4. Right. So now we have to look at each of these terms separately. Right. So let's start with B1. And so we'll have to integrate this formula over this semicircle starting from point A, ending at point B. Right. Okay, so let me look. So let me write section 1. And since these are integral, or I mean these are vectors, so first we will look at direction and then magnitude, absolute value. So let's start with direction. Direction. Okay, D-I-R, direction. And what determines the direction of the magnetic field? This part, ds cross r. And you know what, let me first write the whole integral maybe. No, let me just look at the direction, ds cross r. So that's what determines the direction, ds1 cross r hat. Okay, now I want to see these vectors ds and r on my picture. ds, it's an element of the current. Okay, so now let me draw it here. So I will draw, for example, take this point, and this is my ds1. And again, you remember, direction of ds is determined by the direction of the current. Current flows this way, so direction of ds, right? Tangent, of course. Then, r hat, according to these formulas, r hat shows a direction from ds to the point where we want to find magnetic field. Again, from ds to the point P. So in this case, so this is our segment with the current, and point in question is over here. So r hat should point radially, right? And what is r? This r. It's again distance from ds to the point where we want to find magnetic field. So as a result, my r, this is r, and that is, you see, that is r hat, right? So that is ds1, and that is r hat. Again, r hat, it's a direction. It shows a direction from ds to the point where you want to find magnetic field. That's how that formula is constructed. Okay, so now if we look at this cross section, we have to use right-hand rule number 1 in order to find direction of this cross product. It's a cross product typical. So ds cross r. So first I have to position my hand along the direction of ds, that way. Right? Then I need to orient my hand in such a way so that I can bend naturally my fingers in r hat direction. So I have to position my hand like this, and then I can naturally bend my fingers down, basically, in the direction of r hat. And as a result, my outstretched thumb gives me direction of the cross product. It is into the board, right? In the positive z direction. My z direction, positive z direction, is into the board. So as a result, I can write, so this is into the board, which is plus z hat direction. Okay, so now I know direction, right? And I should be able to write b, right? So vector b1 will be absolute value of b1 and times plus z hat direction. Right. Okay, so now we know direction, we just need to find the absolute value of the magnetic field, the magnitude of the magnetic field, or contribution to the net magnetic field, which comes from this semicircle. Okay, so now just the magnitude. So now magnitude. Now we'll have to do some integration. So b1. So you see, now there is no vector sign. Now it's the absolute value of this magnetic field. So this b1. Okay, so it's an integral. We'll start integration at point A and finish at point B. So integration from point A to point B of db1. Right? So db1, let's just rewrite that. Alright, so we'll have integral from A to B, mu naught over 4 pi, I'm just rewriting that formula, times I, then ds, and these are absolute value, so I have to put absolute value sign over this cross product, because I know the direction. Now I'm just interested only in the magnitude, so I will put absolute value sign, ds1 cross r hat divided by r squared. Alright, okay, so now we need to look carefully at this, right? So what we're going to have here, and I will open my explanation box in order to explain what I do to move from this point to the next point in this equation. First of all, r, this r small in the denominator, r squared, what is that? Again, it's a distance from the section ds to the point where we want to find magnetic field. It's from this point to point P, which is R1, just R1 capital. So R equals to R1. Then, now we need to look carefully at this absolute value of the cross product. Okay, I'm running out of space slightly. So absolute value of ds1 cross r hat. Right. Okay, you remember how can we open, how can we find absolute value or magnitude of the cross product? It's an absolute value of the first vector times absolute value of the second vector times sine of angle between them. Okay, so let's write it. So absolute value of ds, it's a ds1. Absolute value of r hat, it's just 1 by definition. Any unit vector has a magnitude of 1, and times sine of angle. Which angle? Angle between vector ds1 and r. Okay, let's look at the picture. ds is tangent to this semicircle. ds is tangent, but r hat is radial. What's the angle between tangential direction and radial direction? Of course, 90 degrees, right? Of course, 90 degrees. So that is the angle which we need. Theta equals to 90 degrees. So sine of 90 degrees. Sine of 90 degrees is just 1. Just 1. Okay, so as a result, it's still my explanation box. Oops, slightly erased. Alright, so we'll have, this is 1, this is 1. So we have just ds1 left. Just the absolute value of this infinitesimal small section of the wire. So ds1. Okay, let me continue my explanation box, right? Okay, and now let me continue this equation over here. Mu naught, constant, I, constant, 4 pi, constant, can be taken outside of the sign of the integral. Then r, it's just the r1 squared. Again, constant. Again, this can be taken outside of the sign of, outside of the integral. So let me do this extraction. Mu naught I divided by 4 pi. Then r1 squared also goes outside. r1 squared and integral from a to b. And what's left, again, this is gone, left. And out of this absolute value, we have only ds1 left. Alright, ds1. Okay, so now let's look at this integral. What's the meaning? We integrate from this point to that point, ds's. Again, what does it mean, integration? Integration means addition. So what you do, you add ds's. Small ds plus small ds plus small ds plus. You keep adding these small ds's. So if you move from this point all the way to this point, you will get the length of this semicircle, which is half of the circumference. Right? The total circumference of the loop is 2 pi r, but in this case, since we have half, it's a pi r. Okay, so the value of this integral is just pi r1, half of the circumference. Right? And then look, this pi and this pi, they get cancelled. Then one of these r's, r, and this one of r gets cancelled. Right? And as a result, we can write the final value of this integral. It will be mu naught times I, 4 stays, 4 survived, then and 1 r1. Right? This 1 r1 gets cancelled, but 1 stays. So that's the magnitude of b1, absolute value of this contribution, b1. Right? So I can write now the vector b1 just by multiplying this by z. Okay, so I can write, so b1 vector equals, alright, mu naught times I divided by 4r1 in a z hat direction. So that's our first term in this, in the value of this magnetic field. Right? Okay, so we found for the first one. Now, very similar, we're going to take care of B2 then B3 and B4, one step at a time. And okay, now I need to erase this. Now I need this space. All right. Okay. Now second B2. All right. So now that was section 1. Now section 2. All right. Again, I will start with the direction. So first, direction. Alright, so again I need to look at the cross product of ds, but now it's a 2, cross it with r hat. Okay, now let's draw ds2, let's draw r hat on the picture. And so now in this second section, it's this section, you see, this semicircle with larger radius. So, and we move from point C to point D. Okay, so ds2. Let me ds2 draw, for example, here. So to have space for a picture. So let's say that this is my, let me remove this card, draw it here. So ds2, right? And r hat, it shows a direction from ds to the point where you want to find magnetic field, to point P. So, and r itself, okay, let me use a different color, I can use green also. Right, so this will be r, right, distance from ds to the point in question, and this will be r hat, right, unit vector showing direction to the point P. Okay, so ds2 cross r, ds2 that way, r is down, so I have to position my hand like this. ds2 cross r, it will give us direction of this cross product out of the board, which is minus z direction plus z direction into the board, but this cross product again gives us direction out of the board. Okay, so direction out of the board. Alright, so which is minus z hat direction. Okay, so now we know the direction, and I can write that. Oh yeah, let me write it over here. So B2 vector will be absolute value of B2 and times minus z hat direction. So now we just need to find B2 absolute value. And now we'll have to set up a similar integral. Right, so B2 equals integral. Now integration. So this is, we'll start integration from point C, from this corner, and we'll move all the way to this point. So from C to D of dB2. Right? And so now we'll have to write that Biot-Savart law for current. And again, absolute value of that law. So it will have a similar structure. So integration from C to D, mu naught over 4 pi I, and again absolute value of ds2 crossed with r hat and divided by r squared. Okay, now I have more space for my explanation box, but explanation box will be very, very similar. Okay, so let me open my explanation box, and again the same. I will start with r. So this distance from ds to the point P, which is r2. It's obvious from the picture, right? So r2, and then cross product of the absolute value of the cross product ds2 and r. I will open up here ds2 cross r hat, and again absolute value of any cross product. It's an absolute value of the first vector times absolute value of the second vector times sine of the angle between them. So ds2 times absolute value of r hat times sine of the angle between them. And again, what's the angle between them? You see both of these vectors are tails, so both vectors are at the same point. So that is the correct configuration, and as a result, that is the angle which we need to use in that cross product, which is again 90 degrees, because every time the angle between the tangential direction and the radial direction in the circle 90 degrees. Okay, sine of 90 degrees. So absolute value of r hat is 1, value of sine of 90 degrees is also 1. As a result, absolute value of this cross product is just ds2. Okay, so we're getting very, very similar result. So now I can, let me close this explanation box. Right. And also let me take outside all the constants. Again, m naught, mu naught, I for pi r2 squared, all can be taken outside. Mu naught I over 4 pi r2 squared, so all constants. And what's left inside of the integral from c to d? Only ds2. Only ds2. And exactly the same like what we had here. And the value of that integral is just the length of this semicircle now, which is the half of a circumference. So it will be pi r2 square, pi r2. Right. So this will be equal to pi r2. Again, pi gets cancelled, r2 cancelled, and what's left? Only 4 pi I divided by 4 r2. Right? So you see, very similar. And of course it makes sense, right? Right. So I can write b2 now vector. I just plug this into the this. I just want to write b2 in a vector form. So it will be mu naught I over 4 r2 and in minus z hat direction out of the board. So now what we found this, we found that. Now b3 and b4. So now let's look at sections 3 and sections 4. Okay, now let's do section 3 in a very similar way, right? And you know what? I will just write down the absolute value of, and you will see why. So let me do section. So magnetic field b sub 3. Okay, so it is integral of dv3, and what we integrate from point B to point C, right? B, C. Okay, and now let me write again explicitly the Biot-Savart law, absolute value of the Biot-Savart law, BC, and it's mu naught I, then absolute value of ds4 cross r hat, and divided by what, constant for pi, and then r squared. Okay, now I just want to look at this cross product. And of course, in order to look at that cross product, I want to draw ds. It's a 3, not 4. ds3. So I want to draw ds3 and r on this picture. Okay, direction of ds is determined by the direction of the current. Current flows that way. So my ds will be this way. So that is ds3, right? Points that way. Then r hat. R hat gives us direction from ds to the point where we want to find magnetic field. So in this case, so this is ds, and direction to the point P, it's this r hat. So you see, these two vectors are anti-parallel, the points in the opposite direction. Of course, cross product of two anti-parallel vectors pointing in the opposite direction is going to be 0. Let's see. I will open my explanation box and let me just rewrite this part of this integral. So ds3 crossed with r hat, absolute value, right? Equals, again, absolute value of ds3. Let me write immediately ds3 ds3, then absolute value of r hat, which is 1, and times sine of angle between them. What is the angle between them? This vector points that way, that vector points this way, so that is 180 degrees. 180 degrees. Sine of 180 degrees is just 0. Right? So that is 0. So this whole integral is 0. So there is no contribution to the magnetic field from this section number 3. So we can dump this term number 3. Next, section 4. Situation will be very similar, and I will address it in a very similar way. So now let me write section 4. Again, B4. Again, it's an absolute value, and I will write immediately this part. And now in section B4, in the section 4, we integrate from point D to point A, direction of the current. So, integral from point D to point A, mu naught I over 4 pi r squared, and then absolute value of ds4 cross r hat. Just very, very similar to the previous one. And again, I want to see on the picture ds4 and r hat. ds4, again, ds is determined by the direction of the current. Current flows that way. So I can draw my ds this way. So that's ds4 that way. R hat, it's a direction, it shows the direction, again, from ds to the point where we want to find magnetic field. So R hat will be also that way. So R hat will be also that way. So you see we have two vectors pointing in the same direction. Cross product of two vectors pointing in the same direction, parallel vectors, is 0, because the angle between them is 0 degrees. Right. So I will write similar way. So ds4 cross r hat absolute value. Again, it's an absolute value of ds4, absolute value of r hat, which is 1, and sine of 0 degrees. So, which is 0. Sine of 0 degrees is 0. So I can show that this is 0, and the result, this whole integral is 0. And so I can remove the last term. This is 0. Okay, so now we found all these terms. So now we just need to write final result, net magnetic field. Okay, let me separate it like this. And now the final answer. So we'll be just rewriting this principle of superposition. So B equals B1. B1 is here. So it's a mu naught I divided by 4R1 in the positive z direction. So it's a B1 and B2 that with minus. So minus mu naught I divided by 4R1 and again in the z direction. But this minus, you see this minus, I put it in front. Okay, so now everything is given. Don't forget, this is R2. This is R2. Everything is given, and don't forget that radii must be in meters. Let me emphasize on that. So must be in meters, and R2 also must be in meters. So if you plug all the values of this, you will end up with the answer. And obviously this term is going to be larger than that one, right? Because R1 is smaller than R2, and R1 is in the denominator. So the answer will be 7.9 times 10 to the power of minus 5 in the z direction, units of Tesla. Right. Okay, that's the problem. In your homework, you're going to have a very similar problem, but in your homework, instead of semicircles, you're going to have some smaller parts of the circle. But the idea will be very, very similar. You just need to repeat these steps, but with small adjustments. Okay, so now we can look at next examples. Next problem. Let's look let's start looking at Amperes Law. We're going to spend quite some time discussing Amperes Law. Before we start applying that, let's just review what is that and how that can be used. So let me write. So now Amperes Law. Amperes Law. It's one of the fundamental laws in physics in general. Right? It's universal, it's timeless, it can be, you can apply it at any point of time, at any point of the universe, right? So no restrictions. So first, and since it is so universal, usually fundamental stuff like that cannot be derived. So what can I do? I just can present it and we can discuss how that can be used. Right, so Amperes Law, it's an integral over a closed loop. So that is the line integral. Over a closed loop over dot product of the magnetic field and the element of that loop, ds, infinitesimally small section of the loop. And it is equal to our new constant permeability constant mu naught times I enclosed. Okay, so and now let's outline steps that we have to make in order to start using Amperes Law. First of all, first step that you have to make, you have to pick a closed loop. The loop must be closed. If the loop is not closed, you cannot use it in Amperes Law. So first of all, and of course, since that loop is going to be used with Amperes Law, we're going to call it Amperian loop. So first we need to pick Amperian loop. Amperian loop. And again, what is important, it's a closed one. It must be closed. Then you need to pick a direction of integration, right? So when you pick the loop, okay, for example, let's say I pick this loop. Let me use black. All right, so let's say I will pick this loop, right, for my Amperian, for my Amperes Law. And also let's assume that this, for example, current is flowing up. This, let's assume down, I2, and let's say this is I3 also up. Well, just completely arbitrary situation. So as I said, the second step, we need to choose direction of integration. You can integrate this moving this way along the loop or that way, right? So let me pick this way, right? So that's my direction of integration. And after that, yes, so let me write. So then direction. So choose a direction. Right. Choose a direction. Direction. Right. So and then what is I enclosed? I enclosed on the right hand side, it's a total amount of current enclosed by our chosen Amperian loop. In this case, I1 and I2 are enclosed, I3 is outside. We are not counting currents outside, only currents which are physically embraced by our Amperian loop, right? So then 3, I enclosed, total current enclosed by the loop, by our Amperian loop, right? By our Amperian loop. And then, in this case, we have two currents enclosed by the Amperian loop, and one current is up, second current is down. So definitely they cannot enter into our Amperes Law in exactly the same, with exactly the same sign. We have to make a decision which current is going to be positive and which current is negative. So in order to make that decision, we're going to use right-hand rule number 2, which says this. Right, so once you pick a direction of integration, now use your right hand, curl your fingers in the direction of your loop, right? Curl your fingers, and then outstretched thumb gives you direction for a positive current. Right? Okay, let me use this loop. For example, let's say this is our Amperian loop, right? And let's say this is our direction, chosen direction. So just curl your fingers in that direction and your outstretched thumb gives you direction for a positive current. In this case, current I1 is positive and current I2 is negative. So in this case, I in will be equal to I1 minus I2. So these are steps that we have to make every time in order to apply Amperes law. And of course, how to handle this integral, we will look at that in our next recitation class. Today, let's look at the problem, which is significantly simpler. In the next problem, we're not going to find magnetic field. We're going to find one of the unknown currents. And in this case, application of the Amperes law will be very, very straightforward. Right? Again, finding magnetic field, we will do that in the next recitation class. So let's look at the problem 22. 22, again, it's a chapter 29, problem 22. So what is given? We have three currents, right? And I'm going to draw a two-dimensional picture. So I don't remember the numbers. So let's say this one current is this way. The value is I1 is 2 amps, and you see cross. It means this current flows into the board. Then I2 is also given, right? So let's say this is I2, and the value of this current is 6 amps. But this current flows out of the board. Dot, it means out. Then the last current, which is unknown. All right, so we only know the direction is into the board, and we need to find this I3. So that is our unknown, right? We need to find. Then, but it's not the whole story. Somebody was generous enough to give you an Amperian loop with a direction, and even more, that somebody was so nice that gave the value that he gives the value of this integral, right? And we will have to find the value of this current. Okay, so what else is given? The Amperian loop. And Amperian loop is this. So that is our, let me write it here, Amperian loop. And you see it is closed. If you do this, Amperian loop must be closed. Otherwise, it would be illegal to use this Amperes law. Okay, then direction was also chosen or given for us. Let's say this is a direction, right? So it's a clockwise direction. And as I said, the value of this integral is given. So somebody calculated that value. So let me write also what is given, the value of this integral over this loop. Over this loop, right? So b dot ds equals to, what's the value? 3.77 times 10 to the power of minus 6 units. You can easily see units of magnetic field Tesla, units of ds meters. Tesla times meters. Right, Tesla times meters. Right, so that's what is given, and we just need to find I3. So find the value of this current I3. Right. Quite often I give a problem like this on the exam among multiple choice questions because it doesn't require much of efforts to solve this problem. Okay, it's a direct application of the Amperes law. So let me just rewrite it. So we have integral over the closed loop b dot ds equals to mu naught I enclosed. And again, as it's given, the value of this somebody gave us, right? So now we just need to look at these sides of the equation. And so now we have to carefully write this term I enclosed, right? Using that rule. So since Okay, let me rewrite it over here. So 3.77 times 10 to the power of minus 6 Tesla times meters equals mu naught. And now I want to write all currents with the proper signs, pluses and minuses. So since direction is given, right? So once you know direction of this integration, you can make a decision which currents are positive and which currents are negative. You see this rule, choose a direction, and then you can use right-hand rule to make a decision which currents are positive and which currents are negative. Okay, so right hand, curl my fingers in the direction of the loop, and my outstretched thumb gives me direction. Positive direction for a current is into the board, right, away from you. Okay, so it means that current I1 is positive, I3 is positive, and I2 is going to be negative, right? Okay, so now I can write, so minus I1 minus I3, plus, I said, okay, sorry. All right, it's a plus, all right, into the board is positive direction, that is into the board, that is into the board, so these are positive, and then minus I2, right? So given, unknown, given, so, and of course this is given, this universal constant, so basically one equation, one unknown, so we just need to solve it for I3. That's why I told you problems like this quite often I give among multiple choice questions on the exam. So let me take mu naught to this side. So it will be I1 plus I3 minus I2 equals to the value of this integral divided by mu naught, which is 4 pi times 10 to the power of minus 7 Tesla times meters over amps. Right? Okay, and you see units actually matches, right? So Tesla times meters gets cancelled, amperes goes upstairs, and on this side we have amperes, on that side also amperes. So in terms of units, everything is nice. And so now this is our unknown, right? So let's just solve it for I3. So I3 will be equal to I1 plus I3, yeah. I3 will be equal to this ratio 3.77 times 10 to the power of minus 6 divided by 4 pi times 10 to the power of minus 7 units of amps, right? You know what, no, I don't like the way it looks. Right, so just amps, right? And minus I1, right, and plus I2, right? So it's minus I1 plus I2, yeah. So if you plug all the values, you will get 7 amps. 7 amps of current. So current, the value of current I3 is 7 amps. And of course, direction was given from the very beginning, right? So current flows into the board. Okay. So this is a part which can be solved within a couple of minutes, right? I mean, the problem which can be solved within a couple of minutes. In the next recitation class, we will actually start finding magnetic field. And again, the troubles or the problem, the biggest problem with Amperes Law, that magnetic field is buried inside of the integral. If you want to find magnetic field, you might end up having big troubles extracting magnetic field from the sign of the integration. Right. Okay, thank you, and see you next time.